All right, we're going to get started. Thanks for coming out to this last session of the day. I appreciate you all being here. So real quick before I get started, let me just introduce myself. My name is Ian Haken. I'm currently a security researcher at Synopsys, working on Covarity's static analysis tool and other application security tools. Prior to Synopsys, I got my PhD at UC Berkeley in mathematics, and I've also been a professional software developer for about 9 years. If after the talk you guys want to get in touch with me, I'm on Twitter, and old-fashioned email works as well. So should be easy to get a hold of. So today we're talking about full disk encryption. So for anyone that doesn't know exactly what that means, that is exactly what it sounds like. It's encrypting an entire disk or volume, and it's usually handled at a very low level with a driver or at the operating system level so that it will transparently decrypt all of the drive contents for all the applications and services. The services are usually totally unaware that the drive itself is actually encrypted, so this isn't meant to protect against remote attacks. By the time any application that's sending out data remotely sees it, it's already in clear text. So this is specifically meant to protect against threats with physical access. So this talk is very specifically going to be about how you can attack full disk encryption, assuming that you have physical access, whether that means that there's a stolen laptop or a laptop that's been lost, or someone is picking up a laptop that's been left in a hotel room. We're going to assume that the attacker has access to the device. So this talk specifically is about Microsoft Bitlocker, which is Microsoft's proprietary full disk encryption solution that's been built into all versions of Windows since Vista. And it's specifically been built into the professional and enterprise versions. And it has been built to use the trusted platform module that's available on lots of devices. And that is something that I'm going to go into detail in a second, but the TPM in this case is used to store that master encryption key. So this physical chip that lives on the device is what's responsible for keeping that secret. So the TPM is an open specification for an API that can do a lot of different things. And if you're interested in trusted computing, there's a lot of sort of very cool and specialized applications. But it's sort of a fairly general API where you can do a lot of things with it. But in our case, what we're really interested in is how the TPM can be used to store secrets, and specifically in this case, the disk encryption key. So a TPM has a number of platform configuration registers called PCRs, and the specification has like 24 of them, and Microsoft Bitlocker uses about 4 by default. And so I'm not going to go into the specifics too much on what each one is used for, but the idea is that you can load in information to these registers about the configuration and status of the device. And each stage of the boot process is responsible for making some hash of the next stage, whether that's the master boot record or the bootloader, and putting that value into a PCR. And so when a machine is first booted up, it initially has 0 in all of these registers. And whenever any API call is sent to the TPM to update the value, it never sets the values directly. It always takes the old value, concatenates it with the new one, hashes that, and puts that result into the PCR. And this is really important, and this is sort of very critical to how the TPM is able to store secrets safely, because you can't set arbitrary values to the PCR, even if you have like kernel level access to the device. The TPM just doesn't expose the functionality to set a value directly. So after a value is already set in there, you can't set a new one. So only that original boot process where each piece is responsible for hashing the next and putting that in a PCR can reproduce those same values in the PCRs. So when the TPM is told to store a secret, in this case our disk encryption key, you have the option of sealing it. And when you do that, you specify some of the PCRs to use as parameters to that sealing operation. And after a key is sealed by the TPM, it's only going to unseal that key if the same PCR values exist as when it was originally sealed. So when Bitlocker is setting itself up and first encrypting the drive, it looks at the current values in the PCRs, And then only when the machine has been rebooted through the same boot process will it ever unlock that key. So effectively, what this means is even if you have physical access of a device, if you boot into some attacker-controlled operating system, it cannot ask the TPM for the key that's been sealed. And that's a very sort of powerful feature of the way this disk encryption works. And it's also going to be sort of just important to understand that point, that this allows you to securely keep a secret in the TPM without actually having to specify a password, because it's just looking at these PCR values to believe that it is the original boot process asking for that key back. So Bitlocker has the option of using either a PIN or a key saved on a USB drive, but these are optional if you're using a TPM because it can just rely on those PCR values to verify that it is Bitlocker asking for the key. So in its recommended configuration, Bitlocker works transparently. You don't need to put in any sort of password or PIN, and you can just turn on a machine that's been encrypted, and it will decrypt the drive on boot and start serving up clear text to Windows. So if you have Bitlocker enabled this way, you might not even realize that disk encryption has been enabled because it's happening completely transparently when you turn the machine on. So the picture of what this boot process looks like is something like this. And again, this is sort of a simplified thing because the details here aren't too important for where I'm going. But the first part of the boot process, either the BIOS or the EFI, will read in the next part of the boot stage, hash that, and put it in a PCR in the TPM. It then passes off control, and this is going to happen a few times down the chain of control when it boots. But eventually, when you get to the last part of the boot process, it's going to ask the TPM to unseal the key, and it's going to put that key in the RAM so that the operating system in the future can transparently encrypt and decrypt data off of the physical drive. So once that key has been pulled out of the TPR, then it hands off control to the regular operating system, which then begins running as usual. So in this picture, if you're interested in attacking full disk encryption, there's sort of three different boxes that I think of that you could potentially attack. So one is the early stages of the boot process, either the BIOS or the EFI or one of these early parts of the boot system. There are potentially bugs in there where you could cause it to do something it's not meant to do. If the platform isn't set up to require signed firmware, you could put your own firmware on there and do something malicious. There's the physical hardware that you could potentially manipulate. So there's potential to do a cold boot attack on the RAM. There's also been known attacks on TPMs, and I'll say a bit more about that in a second. And then there's the operating system. Obviously, the operating system is the biggest thing here. It's got a very large attack surface. So that's where I'm going to end up targeting this attack. This is saying a lot of basically the same things, but there have been known attacks on the hardware. So I mentioned cold boot as a previously known attack where if you lower the RAM temperature to sufficiently low temperature, it's not going to lose its memory across a reboot. So since the TPM has already released its key and Bitlocker has put that in the RAM, you could potentially reboot into an attacker-controlled operating system and dump out those RAM values before they get cleared from memory. So that's a known attack that people have shown is somewhat effective. There was also a vulnerability discovered in old versions of the TPM specification where you could actually ground some of the pins on the physical chip, and it would cause the PCR registers to get cleared and go back to 0. And then a malicious operating system could then spoof other PCR values, and you could then ask it to unseal a key. Modern versions of the TPM spec have fixed that flaw, but sort of all I'm saying here is that it's not unwarranted to worry about other potential hardware issues. But as I said, where I'm going with this is we're going to attack the operating system itself. So if Bitlocker is set up to boot in this transparent way, then you turn on the machine and it boots up to a login screen. So it's going to look something like this. So that means that logging in to the Windows machine is then our attack surface. If you can get through this screen, then you are logged in as the user and you have access to that user's data. So we're going to attack Windows authentication. So to do that, I'm going to talk a little bit about how Windows Authentication works. So the thing to note from this screen where you're about to log in is that there's something that you probably recognize here, which is that it is showing a login for a user on a domain. And that means that this machine is going to try to talk to a domain controller and ask for that domain controller to supply credentials to authorize logging into this machine. So that means that, again, there is some complexity involved and there's an attack surface for us to try to get through this login screen. So Windows Authentication is handled by the local security authority. And that delegates its authentication procedure to different security subsystem providers. And one of those is used for client domain authentication, and it uses the Kerberos protocol. So when attacking full disk encryption, we're assuming that we have physical access to the device. So if I'm carrying this laptop that's been encrypted, I can plug it into my own network and run my own domain controller on that network and force the login process to talk to that domain controller. So when you log into a workstation that's connected to a domain, the first thing that's going to happen is the machine is going to request for what's called a ticket granting ticket from the domain controller. This is part of the Kerberos protocol. And the ticket granting ticket that the domain controller will respond with is basically a session token that's going to last for the lifetime of that login. And this is what's used as part of this sort of single sign-on on Windows domains so that you don't have to type in your password when you log into any other services. And what's returned with that ticket granting ticket is also a secret that's been encrypted with the user's password. It's assumed that that the domain controller has a hash of the user's password. And when you type in the password to the local computer, then there's also a copy of that password temporarily on that computer. So the domain controller is going to respond with this secret that's been encrypted with the user password, and then the local machine will verify that it can decrypt that secret using the password you just typed in. So this is something that we can completely reproduce with our mock domain controller. We can set whatever password we want on the domain controller to use for encrypting this secret, and we can type in that same thing right here with this device that we're physically in front of. So we can use the same password in both places, and there's nothing wrong with reproducing this part of the login process. But there's a second part of this Kerberos protocol that allows you to actually authenticate that you have permission to log into this particular machine. So after you have that ticket granting ticket and the secret, you then need to request for an actual service ticket that gives you permission to log into that machine. So you send the ticket granting ticket and something encrypt with that secret S to the domain controller. The domain controller does some work and sends back a ticket. And then the local machine has to verify that that is a valid ticket, allowing this user to log into this machine. And again, this is something that we can try and reproduce with our mock domain controller, but there's a complication, and that's machine passwords. So just like your user account has a password, every machine that's registered with a domain controller also has a password associated with that machine account. So when you first join the network, when a machine first joins the domain, it generates a secret key and exchanges that key with the domain controller. So just like your user account has a shared secret in the form of your password, each machine also has a shared secret. And because this device is encrypted, we don't know what that secret is. We can't just read it off the hard drive. And so we can't set up our domain controller with that same secret. So we can try and generate this service ticket T, but that's supposed to be signed with this machine password. And so if we send a service ticket that isn't signed with the right machine passwords, you get this error message when you try to log in. And you can't really read it there, but what that says is the trust relationship between this workstation and a primary domain has failed. So if you try to set up your mock domain controller, you set any sort of arbitrary machine password, this is what's going to happen. So this isn't going to get you through the login screen. But the thing I haven't described yet is what happens when the domain controller isn't available. Let's say you're at a conference and you're using your laptop during someone's talk. You can still log in with your domain password. And that's because whenever the Kerberos SSP verifies that you have logged into the machine, it will cache those credentials and allow you to log in using those same credentials in the future if it can authenticate with the domain controller. So that local cache has to be updated anytime your password has potentially changed. So anytime it sees a valid authentication or anytime it sees that your password has been changed, it will update its cache. So if we could change the password from the login screen, that would allow us to poison the cache with a different attacker-known password. So if we could only change the password on the login screen. Well, fortunately, there's a situation where that becomes possible. If the domain controller tells you that your password has expired, it will then prompt you to change your password. And after that password change has been completed, that local cache gets poisoned, and you can log in with that new password. So you are through the login screen, and you have access to all of that user's data. So what do you do after that? Well, I mean, you're logged in. If you have local administrative rights, you can dump the Bitlocker key out of kernel memory. Although it's kind of moot at this point, you already have access to all the user's data. So you can dig through whatever data is on there. You can drop in malware if this was just temporarily accessing someone's device. You can basically do whatever you want. So now let's try to do a demo. So this is my encrypted machine. I don't know the password on it. If I just try and log in, it's not going to let me. So I'm going to set up my mock domain controller using this super cool package you may never have heard of called Samba. What did I do? All right. I didn't properly invoke the demo gods. Oh, right. I think I know. It's just because I haven't actually configured it yet. All right. So let's configure it to be a domain controller. There it is. So I've already set this in so that the defaults will match the domain that you can just read off the login screen. And then I'm setting an admin password on this new domain. It doesn't matter what it is. And it does a lot of work. Apparently domains are complicated. So then I'm going to restart my Samba service and then set a password for this user account in a way that it will show up as being expired. So here's the big long command to do it. I'm noting the current date. I'm setting the date to 2001. I set a password on a new account, and then I set the date back to normal. There, it's done. All right, so there's my expired user account. And now let me connect this machine to the network, where it will discover that the Miskatonic domain controller is on the network and try to contact it to log in. And I didn't actually spell password correctly. Let's try it again. So there, I'm logging in with that password I just set on the command line. My password's expired. Let's change it to something else, like password 122. Yep, there it is. So, all right, my password has been changed. Awesome. I still can't log in because there's no computer account for this workstation on the domain controller, which is true. I didn't actually set up a machine account for this workstation. But I'm just going to take it back off the network so that it uses the cache. And there's that new password I just set. And it's logging me in. So whatever the user has on there, you can read it. So what does this apply to? So like I said, this applies to Bitlocker if you don't have pre-boot authentication enabled. So as long as you didn't set a PIN or USB key on it, you can boot up to the login screen and you can run this attack. Obviously, this assumes that there is a domain account on that machine that you're logging in as, so it needs to be attached to a domain, and you have to have logged into it before with that account. If you're talking about like a laptop, this is pretty likely that this is the way it's set up. I tested this on every version of Windows that's currently out there. I even tested on XP and Windows 2000, which is sort of moot because BitLocker wasn't added until Vista. But the point is that this flaw in the authentication protocol has always been there. So obviously this is a bypass to authentication. This isn't really Bitlocker specific, but it's really interesting in the context where Bitlocker is enabled. Because if Bitlocker isn't enabled, then you could just boot into an attacker OS and reset passwords anyway. But it does potentially have other valid attack scenarios. So if someone's locked their computer and walked away from it, and you're looking for an attack that gets you past the lock screen a little faster than rebooting into your own operating system, you can execute this attack in a matter of seconds. Sort of I had this set up where I had to read off the domain off of the login screen and set my thing up. But the domain and the username is all transmitted in clear text. So you can set up a piece of software that will act as a domain controller and just automatically reply as though it's that domain controller. You don't have to run a full Samba to execute this. So mitigations. You could use some form of pre-boot authentication. You can follow Tay's advice and use a PIN. Personally, if on my machine, I like using pre-boot authentication. I like that added security. But deploying this corporation-wide, if you're talking about like a enterprise corporate network where there's thousands of laptops in the system, that is something that is really hard to sell. This is from some quotes from Microsoft's TechNet documentation, basically explaining why it's a hard sell to have pre-boot authentication. You physically have to be at machines to reboot them. And so if you're talking about remote workstations, servers as opposed to laptops, if you reboot it, someone has to go into the data center to enter a PIN. That's not really acceptable. And even if you're talking about someone's laptop, if they forget their PIN in the middle of a trip, they can't reset it until they get back on the domain network to get a recovery key from the domain controller. So Microsoft recommends not using pre-boot authentication. So the good news is that Microsoft has released a patch to fix this bypass. It landed 3 days ago. So update your workstations. The patch requires that after it does the old password reset protocol, it does a full authentication with the machine password to make sure that the domain controller also is giving you access to this machine before it updates the cache. So I do want to give an acknowledgement to the Microsoft Security Response Center, who are really proactive about working with me to get a patch out for this issue. So in just a few minutes that I have left, I also want to just kind of reflect on why this attack works. Like I said, this bypass works even in Windows 2000. This is something that's always been part of the protocol and the way it works. And when this thing was designed back in 2000, physical access was total access. Full disk encryption wasn't commonplace. And I don't think this kind of a threat model existed as part of the protocol design, where you can physically access the workstation and the network, and you control the DC, and somehow you're still attacking the local machine. That wasn't part of the threat model. But as Haroon said in the keynote yesterday, we need to re-examine old truths. Threat models change, and this is a perfect example where old assumptions don't apply anymore. So I think that's just a good lesson in this context and others to remember. So these are the Black Hat sound bites for the talk. There's a defects in Windows domain authentication, which means Bitlocker, under the right conditions, can be totally bypassed. All of its protection's gone. But there is an update that fixes this, so patch your machines. That's always the thing that you should remember in security, right? Deploy your updates. And then the last point, that threat models change. So you need to constantly be reevaluating old decisions. And I think that's also, in a way, good news for us, because I think it means that we're never going to be done with our work. So there's always a job for us. So that's it. There's about 5 minutes for questions if you guys have them. Thank you for coming. Any questions? All right. Yes. He asked if it's possible to disable the local cache, and yes, it is. That means, though, that you have to contact the domain controller to log in. So it means that there's no way to take your laptop to a coffee shop and then be able to log into it. You can't take it to a conference, can't take it on a trip. So it is possible, but most people don't, because of that reason. Yes?
Were there any special considerations for setting up domain controller or domain name?
He asked if there's any special consideration for setting up the domain controller. Other than the domain name and the KDC realm matching, no. You just have to type in those right things that you sort of... Yeah, user account, domain has to match. That's it. I didn't have to patch Samba at all. When I first started down this project, I was patching Samba all over the place to always reply, yeah, that's the right password. Yeah, you got it right. And then I found out that I didn't have to do any of that. It is a completely off-the-shelf version of Samba that I'm using. All right, I don't see any other questions. I'm going to be around if anyone... Oh, there's one. Yes. Yeah. I'll try. I'll see if I can break the patch later. I don't know. Now they know about the issue, so it's going to be harder. All right, I'm going to be around if people have other questions. So thank you again.